All right, we're going to start our last unit today. Chapter 21 is about nuclear chemistry. So we're talking about what goes on in the nucleus of a cell. Okay, so the nucleus we know has protons and it has neutrons. Okay, the mass number is the protons and the neutrons added together. So how much that atom weighs, basically. And we know the atomic number is always the number of protons, because we talked before about isotopes where they can have different number of neutrons, but the protons, if that number changes, you've got a different element. And you know, they write the atomic number on top, the atomic mass on top, the atomic number on the bottom, and so on. Okay, so we know the number of protons is always the atomic number. We know the number of protons and neutrons together is the mass number, and they each give a unit number of 1. They weigh a lot less than that, but it's easier. It's kind of like they made up a system and it's all uniform, so it works. Okay, so we know there's isotopes, that all atoms, not all atoms have the same number or the same mass because they have a different number of neutrons. And just about every element has at least 2 isotopes. So a neutron, you know, it doesn't really affect it much in the sense, it just makes it a little lighter, a little heavier. But since it doesn't have a charge, it doesn't mess with any of the electron-proton reactions. Okay, here's one for uranium. Okay, we got uranium-234, 235, 238. Now they will have the same number of protons. I do believe uranium's 92. So that number will be the same, but there's different numbers of neutrons. Okay. So sometimes what happens when the nucleus changes spontaneous, when something happens with the neutrons, they will emit radiation. And so they're radioactive. And you can tell on the periodic table which elements are radioactive. They have a little symbol by them. Okay. When that happens, when they get, when they change spontaneous and they start emitting radiation, they're called radionuclides. Okay. And there's several ways a radionuclide can decay. All right. And I'm going to show you these nuclear reactions, and your assignment will be about these nuclear reactions. You guys don't worry. Some of you guys are like, no, it's not that hard. I promise. Okay, so in a nuclear equation, atoms and charges need to be balanced, obviously. Okay, that's in a chemical, in a chemical equation, you always have to balance them. You have to use coefficients. You have to have the same amount of atoms on each side. In a nuclear equation, the atomic number and the mass number need to balance. Okay, so it's a little bit different. But again, usually it's only by 1 or 2, so it's not so tough. But it's a way of balancing the charge on the atom and the mass number. And again, we're doing it on a very small scale. We're doing it at an atomic scale. So it's not like a chemical equation. Okay. Here you can see the different types of radiation that can be given off by a radionuclide. They can give off alpha, beta, or gamma. Okay. The alpha is a +2 charge. The beta is a -1 charge. The gamma doesn't have a charge. But the weird thing about the gamma is you can see penetrating power. Like you can stop alpha with just like a piece of paper. Beta, you're going to have to, like if you ever get an x-ray and they wear the lead shield stuff. Gamma, look at that, the difference between them. So these are the nature of the radiation. This is a nuclide. It's just like helium. Here you're dealing with electrons. Here you're dealing with photons. So this one's a little different, but I'll show you how to write them up. Okay. So again, I already went through there that we have the alpha decay. And what happens with alpha decay, here you can see you have, we have 4z over x. Basically, this is an alpha particle. It's 4/2. That's the mass of helium. That's the number, its atomic number, and it's helium, and it's going to change. And again, I'll show you how to do these. A beta, what happens is this is what's going to happen. You're going to get not a change in the mass number because an electron doesn't really have a mass, but you're going to get 1 change in electrons. And then there's a positron and there's electron capture. Okay, and again, I'll show you all these in a few minutes here. Okay, they don't really work with the gamma one again because there's really not a change. It's a very, very high energy particle. Okay, so alpha. All right. If alpha decay, what happens is an alpha particle, which is a helium particle actually, it has 2 protons and 2 neutrons. So if you look here, here's uranium-238, that's its mass, here's its atomic number. So what will happen is, if you take away 4, the mass, you get 4, so that you know, 238 minus 4, 234. 92 minus 2, you get 90. With the thorium, if you look on your periodic table, the atomic number of 90 is thorium. So all you're basically doing is you're taking this and you're adding helium to it. So again, 234 plus 4, 238. 90 plus 2, 92. And how do I get thorium? Look in your periodic table. 90 is the atomic number of thorium. Okay, so you just got to look it up. Okay, so note how the equation balances. The numbers work out. Okay, and again, I already did those. So that's what you balance when you do a radioactive or a nuclear decay. You have to make sure that these numbers balance and the numbers on the bottom balance, the proton numbers and the mass numbers. Okay, here's a beta decay. Okay, when you have beta decay, you lose a beta particle, which is really basically an electron. Okay, so here we have iodine 131, that's its mass, and 53, excuse me. 53 is its atomic number. Okay, so what happens if it goes 131, so the mass stays the same, but it loses an electron, so it becomes more positive. Okay, all right, so, and again, if you look on your periodic table, 53 is iodine, 54 is xenon. It's just the atomic number. And again, if you take 54 minus 1, you get 53. There's no difference here, 131, 0, 131. So again, you're just balancing out the numbers. So with a beta, you basically are going to go down, you're going to jump up one element because of the change in the electrons. Okay. Gamma is a loss of a high energy radiation particle. It usually accompanies the loss of the whole nuclear particle. If you look here, so I don't do the gamma one because really that's a total decay of, and there really isn't a formula for them. But then there's one called the positron. Some nuclei decay by emitting a positron, which is a particle with the same mass as, but opposite charge of an electron. So it's kind of like a proton. Well, it really is a proton, but they call it a positron. Okay. So here we have carbon 11. Its mass is 11. Its atomic number is always 6. So if you take this, here's boron. It's down 1. And again, look at the numbers. 5 plus 1 is 6. And these stay the same, 11. Okay? So again, you're just balancing them out. And usually they start with this side and then you go to that side. Okay? So you balance out the numbers. Okay, if they capture electrons, so if they grab electrons from the surrounding cloud, hang on a second. Hey! Sorry about that. Dogs are a little wild today. An electron from the surrounding cloud, it's basically just absorbed into the nucleus, which is really rare, but this is radioactivity, so things are different. Okay, they're not, you know, this wouldn't happen with an electron or an atom that's not radioactive. Okay, so again, if you look at this one, it stays the same. But now 37 minus 1, because the nucleus is going to grab an electron, minus 1, you're going to get 36. So basically you lose 1. So, and again, it's going to go from, look for the atomic number, rubidium is 37, krypton is 36. So you just look up, to find what element it is, you just look it up on the periodic table. Okay, and again, just balancing out the numbers. Okay, so if you're looking at some sources of nuclear particles, okay, the neutron, the proton, the electron, we have alpha particles, we have beta particles, and we have positrons. Okay, here we get, again, we talked about this one. This is a beta because it's an electron. Okay, doesn't change the atomic mass, but it is going to change the atomic number. So 54 minus 1, 53. Here's a positron. Okay, a positron is where they gain a positive electron. Okay? My dogs are crazy today, you guys. Let's see if we can find a better example. Okay, and then here's electron capture. Again, you have a proton, you gain an electron, so 1 minus 1 is 0. It's going to stay the same. And then you just have to look up which element you have. And again, I'll give you lots of good examples because this might get a little confusing when you first look at it. Okay, the thing to remember about the nucleus is it's usually pretty stable. Okay, any atom with more than one proton, so anything but hydrogen, does have inside of the nucleus, you're going to have forces between the protons, and they're going to try to push each other away because they're both positive. You know, protons are positive. So there's this huge force that holds them together in the nucleus. You don't have to worry about the neutrons because the neutrons are neutral. But if you have a big one, like, where you have like 40 protons in there, there's going to be some serious forces trying to push them away. So they have something called the strong nuclear force. The strong nuclear force helps keep the nucleus together. When you're looking at forces in an atom, the weakest by far is gravity. And think about how strong gravity is in our lives. But in an atom, it's a really weak force. The nuclear force is much stronger. To give you an idea of the nuclear force, if you've ever seen, where they dropped the bomb, the nuclear bomb on Japan, and you see the big mushroom clouds, and I'm sure you guys have heard of all the devastation. Basically, what they took is they took a hydrogen atom, or a helium atom. Anyway, and they split it. They used that nuclear force. They opened it up and then they released the energy that's inside. So think about how much energy that is, because look what it does. Nuclear is, crazy, as far as, I mean, a bomb versus a nuclear bomb and the force it has. And it really, what it's doing is it's opening up that nucleus and releasing all that energy that's in there. Okay, so neutrons play a role in stabilizing the nucleus. Okay, so the ratio of neutrons to protons is important. Again, not in a hydrogen because, well, there are some isotopes of hydrogen. So there are some with neutrons, but basically the neutron helps just kind of hold that together because you got all these protons, all these positive charges, and positives don't want to be by each other. We know opposites attract, but there's that nuclear strong force that holds them all together so that they don't, so they stay where they're supposed to. And the neutrons kind of serve as a stabilizing force in the nucleus as well. What do we got? Oh, here's radioactive decay. Okay. This talks about what happens, and we're going to talk more about this. If you've ever heard of like half-lives and things like that, the radioactive nuclei cannot stabilize by undergoing only one nuclear transformation. Sometimes it has to do several. And this is an example here. They undergo a series of decays until they form a stable nucleus. So they're going to keep losing something or adding something until they get to the point where they're stable. Okay, and again, we're going to talk about that more. I don't know how much more we're going to cover here. Okay, there's your magic numbers. I know that sounds weird, but this is like if you start out at 50, it's going to keep reacting until it gets down to 28. You start out at 27, it's going to keep reacting until it gets down to 20. So these are the magic numbers. These are where the neutrons result in your stable nuclei. Okay, I know it's kind of crazy, but if you're at 150, it's going to keep reacting until it gets down. The neutron number is down to 126. Okay, so they've been determined in a lab. There's no magic trick to figure out what they are. So nuclei with even number of protons and neutrons tend to be more stable than if you have an odd number of protons and neutrons. I know, weird, right? But something about the stabilizing force in the nucleus helps with that. Okay. What do we got here? Okay, this might be our last slide. I'm just checking on time here. Nuclear transmutations. Okay, you can cause the nucleus to go through transmutations. You can cause it to mutate so that you have the particle to collide with the nucleus. They have something called particle accelerators. They're atom smashers. They're enormous. I'll show you some pictures of them. But they use strong magnetic and electrical fields to make the particles move faster. And so when they do that, you basically get energy from it. We have linear accelerators. There's something called a cyclotron, which is a D shape, and then there's the cytotron, which accelerates the particles in a circular motion. And that's where we end up. But here's your particle accelerators. Look how huge they are. I mean, it's not just a little container. You can see this takes up a lot of space. Okay, and these are built in certain places. A lot of them, I think the biggest cyclotron is in Sweden, I think. But anyway, these are examples of what they do to make the particles go faster. Okay, and they move faster, then you get more of your